I'm going to pass this over to Dr. Pat Hogan to talk about ocean heat data. Pat.
Okay, thank you, Kirsten. Yeah, a couple of months ago, we had a virtual board meeting where we were discussing possible topics for this uh, for this meeting, and I think it was late July or early August, and I think we were in like the 11th or 12th day of record consecutive heat down here in South Louisiana and Mississippi. And so it just kind of seemed so obvious and appropriate that, marine heat waves should be a topic that would really, garner a lot of interest. Marine heat waves aren't anything terribly new. The topic has been around for a while. Um, I've seen presentations on marine heat waves in the Arctic. I saw one earlier this morning, as a matter of fact, on the Mediterranean. But of course, here we're going to focus on the Gulf of Mexico. And we're fortunate to have four distinguished speakers to give us presentations on this topic. Before I introduce the first one, I'd just ask that we hold our questions until all the speakers have had an opportunity to present. We should have plenty of time for Q&A at the end. We've been given an extra 15 minutes. So I think it would just help the continuity of the presentations. With that, I'd like to introduce the first speaker. That's Dr. Zhankun Wang from NOAA's NCEI, National Centers for Environmental Information, and he'll be talking to us about upper oceanic warming in the Gulf of Mexico between 1950 and 2020. So Zhankun, the floor is yours. Thanks.
Hello, will you drive the slide or can I share my screen?
It looks good to me, but you can share your screen, sure.
Yes.
I just shared my screen.
So can you hit the slideshow? There you go.
There you go. Perfect.
Hey, okay. Hey, everyone. So today I will talk about the upper oceanic warming in the Gulf of Mexico between 1950s and 2020. My co-authors are Tim Boyer, Jim Regan, and Pat Hogan. As Pat said, we are all from NOAA National Centers for Environmental Information. There have been many studies on the global warming, but there were few studies specifically on the warming trend in the Gulf of Mexico. Some previous study either focus on the sea surface warming using satellite SST or focus on the deep water warming using mode observations. The warming between 0 and 2,000 meters in the Gulf of Mexico is still unclear. Researchers have found that warming can affect many aspects of the natural environment in the Gulf of Mexico. And this includes ecosystem changes, intensified hurricanes, the formation of marine heat waves and cold spells, and the accelerated sea level rise. Is there any questions? I cannot see. So in this study, we will first quantify the warming trend in the upper 2,000 meters in the Gulf of Mexico, and then use the heat budget closure to better understand the causes of the warming in the Gulf of Mexico. The data we used are the temperature profiles from the World Ocean Database. This plot plot the spatial distributions of the profiles for every 5 years from 1951 to 2020. As you can see, in most of the 5-year periods, the data can cover most regions of the Gulf of Mexico. So we have a good set of data. The different color shows the different measurements type or instrument used for the temperature measurements. As you can see, the color change shows the evolution of the instruments for temperature measurements. In total, we used more than 192,000 profiles in our analysis. The methods we used is called rhodium pentaidal objective analysis, following Levitas et al. 2012 methods. Only quality controlled data are used. The temperature anomaly is calculated by subtracting of monthly climatology value, so the annual cycle of the data has been removed from our analysis. The data was then grouped into 1D by 1D graded fields and used the objective analysis to fill in the gaps and smooth the data. I won't go through the details of the methods, but the ocean heat content, which we are going to use to quantify the warming trend, can be calculated using this equation, and then the warming cooling trend can be determined by the change of ocean heat content over time. Now let's look at the surface warming. This, which is shown by the red lines for the Gulf of Mexico. As you can see, the warming roughly started around the 1970s, and it has been increased for more than 1 degree in the past 50 years, from 1970s to 2020. The linear warming rate is about 0.193 degree per decade in the Gulf of Mexico, which is much larger than the rate for the global ocean shown by the black line. It's the warming rate in the Gulf of Mexico at sea surface is about twice that for the global ocean. But this rate is comparable to the warming rate estimated from satellite observations reported in the literature. For the subsurface warming and cooling, I show the integrated ocean heat content in this P-color plot, which is a function of time and depth. The linear warming rate is also calculated, shown by the plot on the right. The largest warming occurs at sea surface in the upper 50 meter, and then quickly decrease with depth. All the values are greater than zero, which means warming can be detected at any depth in the Gulf of Mexico. There are also warming, and warming oscillations, which can better show by the bar plot between 200 and 60 meters. The overall Gulf of Mexico warming rate is 0.86 watts per meter square, and this rate is comparable to the global ocean warming rate. So although at surface the warming rate is much larger than the global ocean, but the overall warming rate is similar to the global values. There are also spatial variations of the warming cooling trend, as shown by this full plot. In the upper 50 meters, warming can be found everywhere in the Gulf of Mexico. The western Gulf of Mexico has a larger warming rate than the eastern Gulf. Below 500 until 600 meters, in the northeastern Gulf of Mexico, we even see a slightly cooling trend. So the northeastern the region is less affected by warming between 50 and 600 meters. The rest areas are warming. Below 600 meters, the warming becomes more uniform and can be found everywhere in the Gulf of Mexico. So to have a better understand the controlling factors of the warming in the Gulf of Mexico, we conducted a simple ocean heat budget analysis. The heat storage rate or the warming rate can be balanced by the net surface heat flux at sea surface and the advective heat flux. Gulf of Mexico is a semi-enclosure basin. It only has two narrow straits, the Yucatan Channel and the Straits of Florida, connecting to the surrounding oceans, so which makes it relatively easy to calculate the advective heat flux. The loop current brings warm water to the Gulf of Mexico and advected out through the Strait of Florida. For the heat storage rate, we estimate using the integrated ocean heat content from the objective analysis. The rate is about 1.38 terawatts in the past 50 years and 1.63 between 1992 and 2017. Which is the same period of echo we'll talk about later. So the rate is roughly between 1 and 2 terawatts for the warming in the Gulf of Mexico. To calculate the net advective heat flux, we use this equation where V is the loop current transport. It's about 27.6 plus minus force wheel drop based on the published results. Delta T is the climatological temperature difference between the Yucatan Channel and the Strait of Florida. We estimate delta T from the climatology fields and is about 0.6 degree. Based on that, we estimated the net advective heat flux in the Gulf of Mexico about 40.7. When we compare the two values, we found that the warming rate is an order smaller than the advective heat flux, which also means that the Gulf of Mexico needed to lose heat to the atmosphere at a rate about 38.9 terawatts in order to balance the heat budget. Then we investigate the annual net surface heat flux, which is much difficult to measurement. We look at 4 data products: soda, wave flux, ERI5, and echo, which are the 4 representative products for sea surface heat flux estimate. Soda and wave flux showed positive on an annual basis for the annual net surface heat flux. ERI5 and echo showed negative. All 4 products showed a similar spatial pattern that Gulf of Mexico lose heat to the atmosphere in the northern Gulf of Mexico and gain heat in the southwestern Gulf of Mexico. The echo shows a larger area of losing heat to the atmosphere. Further analysis showed that echo data is the only one that can roughly balance the heat budget. The net surface heat flux estimate from echo is about minus 137.9 terawatts, which is very close to the value that we needed to balance the heat budget, minus 38.7. Echo data is based on a nonlinear inverse modeling framework that satisfies both ocean dynamics and ocean constraints. That might be the reason that echo provides a better heat flux estimate to balance the heat budget. The warming can cause a number of consequences and need more analysis, such as the thermospheric sea level rise it can also change the stratification and mixed layer depth. The circulation might change, and some other changes might occur, like the deoxygenation. So we will continue the study to study the consequence of the warming in the Gulf of Mexico using the data from NCEI. One interesting study we are working on is the accelerated sea level rise that are reported by two recent papers, both published in 2023, that there's accelerated sea level rise after 2010 in the Gulf of Mexico and the southeast US coast. During the same time, the sea surface temperature also showed a speed up increase after 2010, and which might contribute to the thermal steric sea level rise. And we are investigating the contribution of the thermal steric sea level rise to the total sea level rise. In summary, using the data from the World Ocean Database, we quantified the warming trend between 1970s and 2020 in the Gulf of Mexico in the upper 2,000 meter. The Gulf of Mexico warms at a rate approximately twice that for the global ocean at sea surface, but the rate is comparable to the warming rate for the global ocean for the entire Gulf of Mexico. We also found a subsurface cooling trend in the northeastern Gulf of Mexico. The warming in the Gulf of Mexico can be roughly explained by the balance between the loop current advective heat flux and the annual net surface heat flux from ECHO. That's all my presentation. I will hold any questions during the end.
Thank you very much, Zhankun. Yeah, I prefer we hold the questions to the end. Very interesting work and very significant that it's really good to see it in 3D. So thank you very much for that. We're going to move on to the second presentation. That's by Professor Nan Walker from LSU's EarthScan Laboratory. I'll let you introduce the title of the presentation, Nan. Please take it away.
Right. Hello, everyone. I'm Nan Walker, and my co-authors are Alaric Haig. He and I work in the Department of Oceanography and Coastal Sciences at LSU, and we together run the EarthScan lab. I'm the faculty advisor, and he's the computer manager and systems manager. Robert Laban is co-author. He's University of Colorado. He's a sea surface height expert. Patrick Hogan, our host from NOAA NCEI. He's the ocean sciences branch manager there, and his main contribution was in providing some sea surface temperature anomaly maps, very important for this summer. So the background image here is a GCOOS SST image created from the new advanced baseline imager of the GCOOS 16 satellite. That's GCOOS East. So you know that's the weather satellite that we use, and for over 20 years we've been creating nighttime SST composites with this weather satellite. And this is one example in the middle of July of 2023. So you see the middle of the Gulf is very warm, about 30 to 31 degrees Celsius, but we see three distinct upwelling regions, one in the northeast Gulf, one in the western Gulf along the Texas-Mexican coastline, and one along the Yucatan coastline. I'm not sure that one is showing up too well. Anyway, the upwelling temperatures were 24 to 27 degrees at this time. So this is the best view of that upwelling from the season, just as an introduction to the GCOOS imagery. One thing about the GCOOS imagery is that because the composites are made just over one nighttime from over 100 images available from the GCOOS CONUS view, we have very good spatial resolution and not much aliases of the temperature signals. So we can pick up very distinct temperature patterns if they exist at the sea surface. So the objectives of this talk are to investigate the SST data from GCOOS for spring-summer 2023 to assess the spatial patterns of surface temperature structure, the time evolution of the changes, the maximum temperatures reached when those were, and the relationships to monthly SST climatological values. The GCOOS ABI data comes from the Google Cloud, and Rick Hague is going to talk about his programs that grab that data and process it into our SST products. He's going to go into those details later in those 3-minute talks, so I won't go over many of those details. Okay, so our compositing procedure is just over one nighttime. We take the warmest picture element from each pixel location, and from that we create the SSTs using an SST algorithm we developed for the Gulf of Mexico. That was developed using buoy data at 1 meter or less. So we calibrate the SST to within 1 meter of the surface. And we use the 4 micrometer channel, which is what we call the mid-infrared channel. It's much less attenuated or contaminated by atmospheric water vapor. So we have a much better view of the ocean pixels. And because the Gulf is so cloudy, that's why we have to use a lot of images to screen out the clouds and the water vapor. The SST algorithm is highly accurate. The RMSE error, the root mean square error is less than 0.2 degrees Celsius, and the R squared of our algorithm was 0.99. All right, the GCOOS ABI sensor is also much more advanced than the GCOOS GVAR sensor, which I used for over 20 years. And it was the technique that we use has been published in Geophysical Research Letters in 2003. So the new GCOOS has a much smaller pixel. We get much more data, and there's also much less noise in the sensor. All right, so the loop current has been very active since the end of December of last year. It shed a new warm core eddy in late December, and that warm core eddy only separated from the loop current several months later. I'll show you that in a moment. Occasionally we add some stories onto our website about circulation in the Gulf, and this is a screenshot of one of those stories, which I thought was very interesting because it was looking at early season warming, late spring to early summer warming in the Gulf. So what this little article talks about is that here you see the loop current in the left panel. So the loop current at this time is shedding a new warm core eddy, or about to shed one, you see here, but it did not. Over here you'll see 5 weeks later on June 9th, the loop current recaptured the eddy, and it remained attached until very recently. Okay, so here this middle panel is an SST animation that runs for the 5-week period between May 1st and June 9th. So one thing we saw early on, besides the influence of the loop current on temperature, was that the coastal waters around Louisiana were very warm very quickly. In fact, within, let's see, about May 10th to May 17th, they warmed up by about 5 degrees Celsius. So we saw huge rapid warmings along the Louisiana coast, which are attributable to the influx of river water, and it's very buoyant and a very thin lens, and so it warms up very quickly. It isolates the solar energy in that shallow layer and warms up very quickly. So the river water is probably a big factor in warming the northern Gulf. So you can still see this on our webpage, and so welcome to visit that. Now I'd like to show you an animation from early April to early October. So notice how quickly the temperatures are warming in the middle Gulf due to the loop current and off the Louisiana coast due to the river water. The river water initially moves west and then offshore and then towards the coast of Florida. And then the maximum temperatures were in the middle of August, and then we see cooling beginning in late September and early October. So that's a very quick view of what happened, and I'm going to go into the details of that now. All right, so I'm going to show y'all some panels of these GCOOS SST images starting in April. The upper left is April the 4th, then we move to May the 2nd, June the 2nd, and July the 13th. So a quick view of what went on in the Gulf in terms of the warm-up. So here you see in early April, the northern Gulf was quite cool, 24 to 26 degrees Celsius, whereas the loop current was 28 degrees, all these waters, and it was quite warm in the southwest Gulf, as well as the Florida, southern Florida, Florida Bay, and extensions out into the Gulf, very warm, 29 degrees Celsius. Oops, sorry. All right, so moving on to early May, you see that there's been hardly no major changes in the temperature structure overall. So we move to the June image, and here you see the temperatures in the loop current have increased to 29 degrees. Florida Bay is at about 29 degrees. So in the southern Gulf, we've increased about 1 degree, whereas the northern Gulf, we increased a couple of degrees Celsius in that time period. Over here in the northeastern Gulf, we have Tropical Storm Arlene. It cooled these waters in the northeastern Gulf of Mexico, and they remained cool for several weeks after this, although I'm not showing this in this particular sequence. It shows up in the movie quite well. If you want to, you can also grab that movie off of our webpage. So July 13th, you could see there was a lot more warming of like 3 to 4 degrees overall. Although we see that these upwelling regions started, the wind started creating upwelling in these 3 areas in the Gulf. This is the maximum view of the best view of the upwelling during the summer, and it was most pronounced in July. It was very late in forming off of the Yucatan Peninsula. And this upwelling in the northeast Gulf is quite unusual. We don't usually see that every summer. All right, and so now we move to the maximum warming. This panel in the top left is a repeat July 13th to compare with the maximum warming image in mid-August. So here we see temperatures approaching 33 degrees C across the Gulf of Mexico. So everything is at the sea surface is very isothermal. So one thing about the sea surface temperature is, as you know, it doesn't tell you anything about what's going on underneath. So you actually have to have some knowledge or information about, what's underneath. So in the loop current, we know that's 1,000, extends to at least 1,000 meters deep, as well as the warm core eddies. So we know that the sea surface temperature is not representative of that depth, but representative of the surface mix layer, which is probably the upper 50 meters at least. So this was the maximum warming. After that, August 30th, the Gulf has cooled a little bit. Here's Hurricane Idalia, the purple. So this is not cloud masked. So what I showed you in the animation had been cloud masked, but sometimes we work with the non-cloud mask data because the cloud mask, unfortunately, does mask some of the ocean pixels. So here was Hurricane Idalia. The colors are purple because it's looking at cloud top temperatures, which is very cold. So the day after Hurricane Idalia hit that coast of Florida, we see Hurricane Idalia's cool wakes. Here's the cool wake between the the West Florida shelf and the loop current. And here's a cool wake along the western margin of the Florida current. So you can see it was actually much colder water brought up along the edge of the Florida current. And so now we're going to move, again, we're going to repeat the August 31 image and then see what happened about 10 days later. You can see the cool wakes have warmed a bit. And then moving on to a couple weeks later, we can still see the cool wake, although it's dispersed over a bigger area. And some of the cooling has been entrained into a cold core eddy here on the eastern side of the loop current. All right, over off of the west side of the loop current, eddy Atwater. This is a warm core eddy, which started forming months earlier, but it's now separated from the loop current finally. And over here on the bottom right panel, this is a sea surface height image from Bob Laban. So sea surface height, positive is the orange and negative is green and blue. So we see the loop current, it's outlined with the 17 centimeter contour, which is what he uses to quantify the separation of warm core eddies, that particular ISO line. So here's the warm eddy separating, having separated from the loop current, moving towards the west. So one reason that the Western Gulf tends to be a little warmer is that that's where the loop current water ends up, because the eddies typically shed off of the western side of the loop current and move towards the west and die in the Western Gulf. Okay, another way to quantify temperature is to look at profiles. Here we show the temperatures extracted along 88 degrees west, May 2nd and August 11th, the maximum heat day. And here are the temperatures plotted along these profile lines from the northern Gulf to the southern Gulf. Here we see a little bit of upwelling still apparent in the northern Gulf. And here's the upwelling off the coast of the Yucatan, a couple degrees cooler. So the loop current shows up as a little bit cooler than the waters around the loop current. And I believe that's because it's a strong high velocity flow with a lot of mixing in the upper layers, in other words, not stratified, whereas the Gulf waters outside of the loop current are actually very stratified. And Pat Hogan has a lot of data on that, on how stratified that water is, and maybe can share that later. Okay, so if we look at the sea surface temperature anomaly data from June to August, and these are provided by Ellen Bartogilles, I don't know how to say her name, sorry, from NOAA NCEI. We have the June anomaly was overall, the whole Gulf anomaly was 0.53 degrees Celsius. We noticed that we had a cool anomaly where tropical storm Arlene was impacting those temperatures due to heat loss from the wind or upwelling from a deeper layer. Without Arlene's effect, the Gulf might have been on the order of 1 degrees. Very warm waters off the Campeche bank because the upwelling was not as prevalent in June as normal. The Florida Bay region looked much warmer than normal. Moving to July, the overall temperature anomaly was plus 1.1. Warmest waters in the Florida Bay region and along the Louisiana coast due to the river discharges. In August, the temperature anomaly was positive 1.17, with the warmest anomaly here in the northeast Gulf and a bit of the north central Gulf, possibly due to the proximity to the land anomaly, which was related to an abnormal high pressure and also due to the river discharges. So this data was from the OISST product, which is at a 25 by 25 kilometer spatial resolution, much less spatially detailed than the GCOOS data. All right, so this was a preliminary study. Not very much time was available to put into it, but I just wanted to share some observations and thoughts about what we saw in the SST data and to relate it to the circulation that was also viewed. So one thing we saw in terms of drivers of the rapid warming and the positive SST anomalies, the presence of loop current water and the separation of warm core eddies is very important to the rapid warming and the eventual temperatures that are experienced in the Gulf, especially in the Eastern Gulf and the Western Gulf, not on the continental shelf. The amount of waters that provide stratification, such as river waters, is very important. We didn't really have an abnormal amount of river water compared to normal, especially in the summer, but it can spread, because it's shallow, it can spread over a big area, and we saw that, and we saw how rapidly it heats up. With a more high pressure air in the area, we would have fewer clouds and weaker winds, and both of these would tend to increase the surface temperature. Okay, and in terms of Florida Bay, we know that the depths are very shallow, which makes it prone to rapid heating. If the wind decreases or we have less clouds, we're also going to have a very rapid increase in temperature. So also it has more solar radiation as a consequence of where it is in terms of latitude. So one question that can be asked is, why wasn't the sea surface temperature anomalies, why weren't those anomalies higher than 1 degree Celsius? And one of the answers to this could be that we know that water has a much higher heat capacity than land, meaning that it takes a lot more energy to change the temperature of the sea surface relative to land. So land is going to heat quicker and cool quicker than the sea surface. Also, the input to water is spread over many meters in the vertical, as opposed to land. So land heats up quickly at the surface, and then the land temperature is basically transferred into the atmosphere above it, giving us the warm air that we experienced over land this summer. Also, the atmospheric anomaly that we experienced over land might have been a little less extreme over the Gulf. So those are my thoughts, and we intend to keep moving towards understanding these sea surface temperature anomalies and how they related to the atmospheric anomaly with additional research. So I'll take the questions later. I'll be happy to answer anyone's questions. Thank you.
Thank you, Nan. Very interesting, and that real-time data is so interesting to look at. We're going to move on to Dr. Brian Dzwonkowski from the University of South Alabama, who's going to talk to us about marine heat waves in the Gulf of Mexico. Brian, the floor is yours.
So yeah, thank you for the introduction. This is a collaborative work from a bunch of different people. It's sort of an overview of things that have come across my radar in terms of marine heat waves in the Gulf of Mexico. If I don't talk about your paper, I apologize. Send me an email. I'm very interested in this topic. And so I just want to give a sense of what I've been seeing related to marine heat waves in the Gulf of Mexico. And this first image you can see in this plot is a product from a NOAA agency. And it's sort of real-time information on marine heat waves. And so this is from this morning, basically. You can see that over the last 30 days, the Gulf of Mexico is still experiencing excessive heat we're sort of in a marine heat wave right now over the entire Gulf of Mexico. And so hopefully that's some motivation for this getting more information about marine heat waves. And so before I get into the depths of this talk, I want to just make sure everyone's sort of on the same page. And so we can kind of just give a little definition of marine heat waves and then talk about why they might be important to us. And so typically, the typical definitions you see in the literature, marine heat waves are typically defined as 5 days above the 90th percentile. Another definition that's sort of gaining popularity right now is sort of a monthly period above the 90th percentile. And to determine the 90th percentile, one needs to have a long-term data set in which you can define a climatology, right? And then then you determine the 90th percentile based on deviations from that climatology. And I think, as many of us know, finding long-term records of ocean data, particularly subsurface ocean data, can be very challenging. And so a lot of the marine heat wave works are focused in on sea surface temperature, where we have, some odd 40 years of satellite-derived sea surface temperature data. And the number of long-term time series of subsurface data that are available to the oceanographic community is very limited. And so that's sort of a topic of interest as well. But why we can consider, why we should be thinking about marine heat waves is because a lot of studies have demonstrated that marine heat waves are associated with extreme weather and impacts to ecology. And if you combine impacts on weather and impacts on ecology, you have economic impacts. And so these types of events are having economic impacts on coastal stakeholders. And so we should be aware of them, and we should try to better understand, and I would argue we should be better aware of them, as well as what are the potential implications on different coastal areas and different coastal habitats. And so hopefully with that sufficient level of motivation, we'll dive into what we're seeing in the Gulf of Mexico. And so some recent work that just came out in 2023, looking at marine heat wave characteristics in the Gulf of Mexico. What you're seeing here are 4 plots of characteristics of marine heat waves. So in the top left plot, you see marine heat wave days. The top right plot, you see duration. Below that, you see frequency and intensity. And what I hope is clear here is that there's a dashed line going through each of these lines. And that indicates since the 1980s to present, you see an increase in all of these characteristics, right? So all of the characteristics of marine heat waves are getting more severe over the last 40 or so years. And so if we look a little bit more granular perspective, we look at the spatial structure of this, we see that focusing particularly on intensity, so how strong those marine heat waves are, there's a significant spatial structure to them, where the northern Gulf of Mexico has more intense marine heat waves than the southern Gulf of Mexico. And that's sort of, you can see that in the plot to the left. If you look to the plot to the right, this is the trend in intensity, so the rate of change of intensity. And what you can see is there's an increase in intensity in the northern Gulf of Mexico as well. So we see the most intense heat waves, as well as the highest rate of intensity increase in the northern Gulf of Mexico. And so why does this area matter? Well, for those of us that live in the northern Gulf of Mexico, we are all familiar with hurricane season, right? And so there are a lot of storms that come into this area and make landfall in this region. And so there's an opportunity for interaction between extreme events, right? Where we can see hurricanes being extreme events and these marine heat waves being an extreme event. And so if we want to try to understand some of these interactions, we need to study both of these processes, or both of these phenomena. And so there is a growing number of examples of the coupling between marine heat waves and tropical cyclones. And again, this is probably not surprising. We've known for decades that high sea surface temperatures are linked to more intense tropical cyclones, right? And a particularly notable example of this would be Hurricane Michael in 2018, where we saw this storm go from a Category 4 to a Category 5 over a region of the Gulf of Mexico that was experiencing a marine heat wave. Another thing we also know about hurricanes and ocean interactions, it's not just the sea surface though, it's the subsurface conditions that matter. So one of the things that I've been very interested in trying to better understand the sort of marine heat waves over the full water column, so sort of extreme heat content events. And so Hurricane Michael was a good example of an opportunity that we could use some long-term time series of the full water column that we have in the Mississippi Bight. And so some work that we looked at prior to the arrival of Hurricane Michael looked at a sequence of events that preconditioned the coastal waters to be at an extreme heat content state. So the plots on the left here show you the red is Tropical Storm Gordon, the magenta track is Hurricane Michael. The plot underneath that is water column temperatures from that site CP on the 20-meter isobath. And then the cartoon to the left, or excuse me, the cartoon to the right is sort of the processes that played out prior to the arrival of Hurricane Michael. And what we saw happen was this sort of baby storm, Tropical Storm Gordon, comes through the area, takes this really warm upper ocean, mixes that heat downward, and homogenizes the water column. Following that event, we see an atmospheric event. We see an atmospheric heat wave rewarm the upper ocean. And so between the mixing associated with Tropical Storm Gordon and the subsequent reheating, we get a sort of stacked thermal structure in which we have extreme heat content during this event. And so these sort of full water column marine heat waves are something I'm really interested in because of their connection to potential for storm intensification. So I have a graduate student working on another event in 2019. Dev Rao is working on another storm event in which we see a marine heat wave, a large scale marine heat wave in the Gulf of Mexico. So the top two plots show the extent and sort of magnitude of this marine heat wave. And if we focus in on the evolution of the event, so I sort of, Dev has sort of produced a sort of cartoon of what the modeling data indicates. And what we saw was it was surface trapped initially. It transitioned to this depth average event. And then over time, it decays into a bottom trapped event. And so we tried to figure out what are the processes playing into this structuring of this marine heat wave, and sort of the details of this, the general processes is it starts out just like a lot of marine heat waves or a lot of surface marine heat waves where it was incoming solar radiation and warming conditions heating up the upper ocean. But then we see a combination of downwelling and mixing that homogenize the water column and create sort of a depth average marine heat wave. Over the life of this event, what we see happening is there's a combination of outward surface heat flux, as you might expect, cooling the upper ocean, but because there's this interaction with buoyancy-driven river discharge, we see that this mass of warmer water gets trapped at the bottom, and so we have a bottom trap marine heat wave persisting for another week to 10 days after the full water column marine heat wave fades. And so if we want to think more about the decay of marine heat waves or ways to mitigate marine heat waves, following some of what Nan was talking about, the summer of 2023 represents a nice example of this, where if we look at sort of OISST and we look at sort of the where there was marine heat waves going on in the Gulf of Mexico this summer, August and July and September all would suggest there was marine heat waves occurring over the entire Gulf of Mexico. But if you look at the details of these, if you look at higher resolution imagery, so right now this is sort of a sea surface temperature image around the northern Gulf of Mexico, the Florida, Alabama region. You can see the sort of bright red colors indicating slightly lower temperatures in and around the coastline, which is indicative of upwelling. And so we were able to go out and collect a whole bunch of data, and we also have a mooring out there in this region. And so if we look at a CTD cast from August 15th from the shelf and compare it to September 8th, we see a dramatic change in the structure, where in August, where we're still experiencing this upwelling, we see a delta T between the surface and bottom of about 6C. And August 8th, after this upwelling has passed, the same site has a delta T of about 0.6. And so obviously there's a very dramatic shift here, as we might expect as we transition out of upwelling, and the whole water column is at an elevated state of high thermal conditions. So these are a lot of physical processes, but there are also some biological implications associated with marine heat waves. And so some colleagues that I have at the University of South Alabama have been looking at the interaction of extreme temperatures with oyster recruitment. And so what these folks did was they took a long-term monitoring site that we have in our local region, our ARCOS network, which is supported by GCOOS, in part supported by GCOOS, has about 12, 13 years worth of data. They coupled this water data with air temperature data from the Mobile Regional Airport, and this allowed them to look at a much longer time period of extreme events and couple that with oyster recruitment data. And what they found is when there is extreme air temperatures, which correlate well with extreme water temperatures, there's a significant impact on oyster recruitment. And so when you have consecutive days of an excessive heat threshold, what you see is a high probability for poor recruitment. It was something like 80% of the times when you exceed this threshold, you get a poor recruitment year. And that apparently in the biological world is an extremely high relationship. The cause of this correlation is not certain, right? There's a lot of things that could be affected by intense heat. And so they're still sort of figuring out what the mechanism is that sets this correlation up. But it's such a strong correlation that there's potential for it to be a management indicator where if you get these extreme conditions, you know the following oyster year is probably going to be a bad one. And so they're really excited about this work. And I'm actually really excited about this work. I think it's really cool and provides some additional motivation to be looking at marine heat waves. And so there is these potential for economic impacts from these marine heat waves. And so how do we continue to provide information about marine heat waves to stakeholder communities in the coastal zone? And so I think if we're trying to convey information, certainly sea surface temperature is a very effective way of identifying marine heat waves in the surface. But this can be problematic in coastal environments where high resolution is needed. It also doesn't give us information on subsurface conditions. And so there's a significant lack of data in general. And so how do we fill these gaps? Well, a couple possible ways might be to maintain existing long-term time series where we are in coastal regions and when we do have depth measurements over long periods of time. Another potential way would be to start looking at glider endurance lines where we collect data over a transect regularly. Potentially expanding Argo float efforts or other type of floats in the deep Gulf. And then obviously sort of modeling might be another approach to try to get better information on some of these in situ data challenges. And with that, I will just thank a lot of folks that maybe I didn't get to mention, certainly Dolphin Island Tech Support Group, as well as various funding sources that have supported work related to this effort. And thank you.
Thank you very much, Brian. Really interesting, really neat to see, not neat, but very profound to see the the biological implications of that. I'm sure you'll have some questions about that. We're going to move on to our last presentation. So last but certainly not least is Dr. Nick Shay, Professor Nick Shay from the University of Miami's Rosenstiel School of Marine and Atmospheric Science, or RSMAS. And Nick, why don't you bring us home, please?
Okay, Pat, first and foremost, thanks for the kind invite. And this is a topic near and dear to everyone's hearts, obviously, with heat in the Gulf. It's not just heat in the atmosphere, it's heat in the ocean. Could you hit the space bar, Jennifer? That's the warm pool of the Caribbean Sea. The warm pool of the Caribbean Sea plays a big role in what happens through the Yucatan Straits and in the formation of the Gulf of Mexico loop current and its subsequent eddy shedding. Hit it again, please. Hit it twice. Yeah. So that's the Caribbean warm pool. And it can heat up to pretty high levels during the summer months. And typically, it's order 80 to 120 kilojoules per square centimeter. That's how we measure the upper ocean heat content. So this upper ocean heat content is a little different than what you heard previously. This upper ocean heat content was developed specifically for the Hurricane Center in response to Hurricane Opal back in 1995, where Opal explosively deepened out over the Gulf of Mexico, caught forecasters by surprise, went from a Cat 1 to a Category 4 over a huge warm core eddy that had spun off the loop current several months earlier. So this is work that's in progress with one of my new students, David Noonan, and we're going to explore a little bit about not just the ocean, but also the atmosphere. Next slide. By the way, this ocean heat content is a 25-year evaluated heat content. In other words, every year we keep evaluating it to make sure that we get something that looks like reality with mixed layer depth, depths of the 26-degree isotherm, depths of the 20-degree isotherm. So like I said, it's a little different. This fellow by the name of Leeper, back in 1972, developed this whole idea about hurricane heat content. He actually was at the Texas A&M University at the time when this was developed. So the approach is to find the depth of the 26, find the depth of the mixed layer, and determine the OHC using the SSTs. This has now been published in several papers, so I'm not going to belabor the point, but there's an operational product that we produce every day. It brings in the SSTs from space. It brings in the altimetry, blends the altimetry from numerous altimeters to try to get the best estimate of the coverage of this, the surface height anomaly field. It is used in forecasting intensity. One of my former students used this way back when, and at the turn of the century. I always like to say that. Makes me feel a little bit more older. And there's a research product that we experiment with different SST products to try to understand the sensitivity of the SST products on the actual calculation of ocean heat content to the depth of the 26. So this is different from some of the other work that's ongoing with ocean heat content, taking it to 1,000 or 2,000 meters. Specifically, the Hurricane Center was interested in trying to understand how much heat is available for the hurricane in that upper layer. Products are evaluated using all sorts of measurements, gliders, floats, moorings, expendables. Thus far with our products, almost 2 million observations have been used to evaluate it per se. Next slide. But before we go into the details of ocean heat content, I want to point out that we are in an El Nino year. We've had an El Nino year in 2015. We'll explain that momentarily. We had an El Nino year not nearly as energetic as 2015 and 2018. And looks like we're midway in an El Nino this year. So I'm trying to understand El Ninos and how it might actually impact the Caribbean, the main development region, as well as the Gulf. Next slide. So back in 2015, we had Hurricane Patricia. Hurricane Patricia was one of these rapid developers, went to Cat 4, Cat 5 pretty quick. So the upper panels represent SST, upper left, ocean heat content in upper right. And then this year, I plotted what it was a couple days ago for the SSTs. East Pacific is still kind of warm, but you also see that the El Nino effects on OHC isn't nearly quite as pronounced as it was in 2015. Perhaps that will change over time as we get into later on in the year. But the point is that when you go back to 2015, those levels of OHC during that El Nino event were about 2 to 3 times higher than normal compared to non-El Nino years. Next slide. Now, one of the things that has intrigued me is trying to understand the correlation between Niño's sea level pressure and what's going on in the Caribbean, in the Gulf, and out in the main development region. So this is from NCEP NCAR reanalysis, and you can see that the August to September correlation, it looks like it's a positive correlation here. Normally in an El Nino year, we expect high pressure in the tropical Atlantic. And we also see some sort of a shifting of the Walker circulation that helps communicate between the bases. So this is for this year, the correlation. You can see the correlation is positive. Next slide. I'm sorry, that was for the previous, that was not for 2023. That was over a longer period of time. But now here's a composite anomaly looking at the 2023 sea level pressures, and now they're negative. So that it's negative instead of being positive. So what does that mean in terms of activity in the atmosphere? What does it mean in terms of what's going on in the Caribbean warm pool? And more importantly, what's happening in the Gulf of Mexico? Next slide. So this year, we've had Felipe, we've had a number of storms that really hasn't penetrated too far to the west, except for Adelia, which made it into the Gulf. We had Ophelia along the eastern seaboard, but this is Felipe. So Felipe got pretty close to the Caribbean islands. The Caribbean islands are in that main development region that we're accustomed to seeing, that the Hurricane Center always talks about. But what did we see in Felipe that was different from all the previous hurricanes? Felipe got a little bit further west and experienced a lot of shear. I think Felipe finally made landfall in New England or the Canadian Maritimes over the weekend. It was a storm that lasted seemingly forever, but it really lost its development when it encountered this enhanced shear. And that's usually what you see during El Nino events. A lot of enhanced shear over the Caribbean warm pool and the main development region. So there's always this question about atmospheric shear, ocean heat, SSTs, what's going to win out ultimately for storm intensity. So it's this push and pull depending upon how strong the storm gets. If there's a lot of shear, typically shear will win out. If there's a moderate amount of shear, ocean might actually win out in some cases. So what is that push and pull, number one? And number two, what is that key threshold? Where is that threshold? A lot of models predict intensity change, but we still don't have a reasonable threshold about what is that parameter space in which we have to really understand shear in the atmosphere versus what's happening in the upper ocean. Next slide. So I went back a few years, non-El Nino years, 2019, 2020, 2021, and 2022, and pulled out, this is on the 6th of October, just to see what was going on in these regions. Again, focus in on the Northwest Caribbean because the Northwest Caribbean basically provides the fuel for the loop current. It also provides the heat for the loop current as it makes its way into the Gulf and sheds warm core eddies. So you see some evidence of high ocean heat content, typically on the order of about 100 to 110 kilojoules per square centimeter. In the Northern Gulf, you can see that it's a little cooler during some of these months, probably because of tropical cyclones moving over and cooling the upper ocean. And you also see evidence of the cycle of the loop current during these 4 years. Next slide. So then we went to 2023, as well as the other El Nino years. And this year, 2023, notice the ocean heat content levels in the warm pool. Significantly higher, much broader, on the order of 150, 160 kilojoules per square centimeter, which is a lot of heat. I want to remind you of some of the early work of Leeper again, since he was really the father of all of this. He said you only needed 17 of these units in order to intensify a hurricane. 17. So you're an order of magnitude more. That's pretty darn significant. So how does El Nino do this with respect to the warm Caribbean pool? How does it affect the Gulf? That's still some open questions that my student and I are beginning to explore with the 25-year evaluated data set. But if you look at the typical CTD data, the temperature salinity profile, you clearly see what's going on here with the warm Caribbean pool. You see the subtropical water, which is indicative of that water coming through the entire Caribbean basin, making it up to the warm pool and then making it into the Gulf of Mexico. So how does this all work? That's what we're trying to explore. So this is really a work in progress. Next slide. And so this was just some of the ingredients that went into this, the SSTs. We use the NESDIS geopolar blended field for the SST for the operational product, because this product was transitioned to NESDIS several years ago. We infer the mixed layer depth. The mixed layer depth is good to within about 5 to 7%. Typically, you're seeing about 50 to 60 meters in terms of the mixed layer depth, as Nan alluded to. But the depth of the 26, typically 140 to 150 meter depth for that. And then the OHC typically follows suit and scales essentially with the depth of the 26-degree isotherm. So understanding where that depth of the 26-degree isotherm is really important for forecasters, because they want to make sure that they can get a good forecast for any storms that might be getting into the basin. And as someone alluded to earlier, the Gulf, the Caribbean, these are semi-enclosed basins. So once a storm enters them, there's a very good chance there's going to be a landfall somewhere, and they will likely get energized. Next slide. So the evaluated product, it's now close to 2 million profiles in the North Atlantic and North Pacific. These are well published. Subtropical water mass is transported through the Yucatan Straits, forms a loop current core. I also want to say something about the Gulf Cores experiment that's coming up, where we're going to be putting gliders and a float into that area along the western side of the Straits, and hopefully it gets into the Gulf of Mexico. The floats that we deploy are a little different than Argo. Our floats actually measure currents all the way down to 2,000 meters, the horizontal velocities, that is, as well as the temperature and salinity. Why, you say? Because we want to measure ocean shear. Ocean shear is important for some of the topics previously raised, like mixing. Shear-induced mixing plays a big role in trying to understand what's happening with the SST responses and how that SST response may actually be affecting the cold wake that we often see. It also allows us to deduce something about the three-dimensional upwelling that actually occurs. That's why we use the Apex E&M floats. The anomalies in the warm pool are typically about 30 kilojoules per square centimeter higher this year than normal. Not quite understanding the full scope of it, but it's a much broader area compared to other even El Nino years. So what's going on there with respect to the El Nino and its potential impact on what happens in the Gulf of Mexico? And finally, there is correlations to the sea level pressures. And when this Walker circulation shifts, subsidence and rising of the atmosphere has a pretty pronounced impact on things like shear and what's going on in the main development region. Next slide. And need I remind this audience, much to my dismay, that we got through the first peak, but mid-October is usually a second peak for the Gulf of Mexico for late season storms. So we're not quite there yet, but we're hoping we get there without incident. Thank you.
I will second that, Nick. 10 more days to the second modal peak, I guess. Thank you very much. Very interesting, of course. I know that we got a little bit of a late start and ran a little bit over. We're at the break time. I would ask Kirsten and Jorge, maybe those interested in asking questions can do so during the break, and those that need to, take the break can do so as well, if that's agreeable to you. So if it is,
I would say let's do at least like 5 to 7
10
minutes of
minutes.
questions.
Okay.
Shift our break a little bit later. I think we've got time.
Thank you. So are there any questions to begin with? And I guess the best way to do that is to raise your hand and speak up, or we can look at the chat as well.
Stephen?
Yeah, a lot of, they were all very interesting, and I have a lot of questions, but I'll just try to leave it at a couple. One is related to the upwelling in the Northern Gulf in July. It also seemed like salinity was really high on the east of the Delta, and that it seems like, I haven't analyzed it, that the Mississippi River was also pushed to the east for a longer period of time this summer, associated with that, that upwelling that you see in the Northern Gulf east of the Delta. Did you notice that, Nan?
Well, like you say, it's a normal phenomena for the wind to blow the Mississippi River water towards the east, towards the Mississippi Alabama shelf. I have not looked at the details of that. There was less river water, in late spring, summer than usual. It's been quite low, but it's still a major river that's still discharging all the time. So, it's a major source of fresh water. But you said you noticed higher salinities, you said, which kind of maybe because of the upwelling.
Yeah, I'm not sure.
Yeah, that upwelling was pretty amazing in July. But then by August it was diminishing a lot. The Mississippi River water is moved around by the wind. So if the wind is, blowing more out of the west for a longer period, it's going to move, for a longer period towards the east. And it's strange because it's colder than the Gulf when it exits the river, but it soon warms up to be some of the warmest water in the Gulf. So it's an interesting transition from colder to warmer very quickly. But I haven't looked at any data on salinity, and I've really not looked at the wind data either.
All right.
Yeah, I mean, Stephen, just to follow up on that, just living on Dolphin Island, just swimming in the Gulf of Mexico in this upwelling was delightful, right? It was noticeable. I mean, it was shockingly cool for that time of year, just by touch, right? But yeah, I mean, I would agree. Like if just looking at the wind normally switches back and forth where it's upwelling, downwelling, upwelling every 5-6 days. It was persistently upwelling favorable from July through August, which, as Nan highlighted, is a little bit anomalous. Usually it's a little bit more variable. And so we didn't get that variability. It was just the persistent upwelling favorable winds, which I agree with Nan is pretty unusual for this time of year. I haven't looked at it from a climatological perspective, but just that was definitely something we noticed.
Just looking at, our buoy data off of Louisiana coast for this year compared to every year since 2017, salinity was much higher.
Yeah, I mean, and then also the salinities at the mooring sites that we have here, definitely there's a lot more saltwater species moving into the bay and things of that nature from like an ecological perspective. It was pretty interesting.
Right.
Well, if you're comparing it to, just previous years, the salinity, the Mississippi River has had a lot of floods in the last decade.
Right.
So maybe, and as I said, it was very low recently, in the summer, etc. Even the spring flood wasn't really up to the normal. So maybe the lack of river water might actually explain your high salinities, possibly. I have a question for you guys, for the Mississippi, Alabama, Florida Panhandle crowd. So there were deaths because of strange currents, offshore currents, like they called them rip currents. Did y'all? I assume you heard about that. I wondered if that had anything to do with the upwelling and the interplay. Well, it must have been a strong wind producing the upwelling. Did the upwelling currents have anything to do with those rip currents that occurred?
Yeah, I'm not sure. I did get that in the news that there was a significant amount of drownings, but
Yeah,
I'm not sure if what the coupling was, if there was any.
right.
Yeah, I mean, just looking at the winds and the waves, you could get a indication of that. But I haven't looked at that.
Yeah.
Rip currents are notoriously small scale,
Yeah.
Right.
whereas upwelling regimes are much larger scale. So, but that has
Yeah,
to do
that
Yeah.
is
with changes in topography as well as prevailing winds. So
right.
it depends on that small scale variability. We have
Yeah.
a lot of problems with rip currents down here when we get
Mm,
those types of winds.
mm. Also, weren't there more shark attacks this year?
I was going to say, I mean, I fish off the Chandelier Islands off of Louisiana quite a bit in the summer, and we saw more sharks out there this summer than we have in the
Yeah.
last 5 summers, I'd say. It's just anecdotal, but man, there
Right.
were a lot of sharks out there.
Right. And so you wonder if that was related to the upwelling in some way. I don't know. Would be interesting to try and get more information on that.
Sharks do
Yeah,
like depth of the 26-degree isotherm. Published. They do.
They do?
Sharks and tarpon in particular, they follow the
Okay.
26-degree C isotherm. We published a paper 2 or 3 years ago on this,
Hmm.
but sharks seemingly like 26-degree water too. Not
Hmm.
sure why.
this was warmer than 26. We were in shallow water. We were surf fishing out there. But
Oh,
they're
okay.
following up and coming into the shallows, I'm sure. So,
Hmm.
are there questions from anybody else in the audience before we go to break?
Yeah, I'm sorry, Stephen. Yeah.
No, it's all right. Go ahead, Brian.
Zhankun, I was curious if you had any thoughts. I saw your presentation. You saw a distinct north-south cooling, right? Like it was much cooler in the rate of heat, the heat flux, right? Was much cooler in the northern Gulf of Mexico versus the southern Gulf of Mexico. Was I looking at that correctly?
You mean the annual net surface heat flux?
Yes.
Yes.
And so I found that very interesting because if you looked at this recent paper that came out looking at trends in marine heat waves, it looks like the intensity is all concentrated in the northern Gulf of Mexico. And so I found this striking, the contrast between where the net heat flux was sort of in the southern, yet the trends in the intensity of marine heat waves was all focused in the northern Gulf of Mexico. And I wasn't sure if you had any thoughts on that.
Yeah, I think that might be related to the advective heat flux. So the heat the vector from south to north, and then cause the intensified warming in the north. That's my guess. But I think we need more current measurements to confirm that.
Thanks.
Stephen, why don't you take the last question and then we'll call it the end of the session and go to a quicker break.
All right. Yeah, my question is for Nick, and the ocean heat content product and the the 17 kilojoules per square centimeter. That was the amount of heat flux. I mean, so that's what you need to drive the intensification, but you really need like 50 kilojoules per square meter because of the cooling? Is that
Basically, the 17 kilojoule per square centimeter per day value came from LEAPR a long time ago.
right?
Now, the problem with LEAPR's work is he took a ship out before a hurricane, and then about a week later, he took a ship out after a hurricane. Okay. He missed a lot of the physics that went on in that whole week.
Yeah.
What we are finding is that the threshold to intensify a storm is probably somewhere in the vicinity of about 20 to 30 kilojoules per square centimeter. That's a lot of heat.
Mhm.
Now, the problem is a lot of these regions have so much heat that you have a storm going over the loop current. Is it going to cool? Not much.
Hmm.
Isotherms are so deep that, I mean, we saw Katrina and Rita, right? I mean, Katrina went over the loop current over a warm eddy. The SST response on the perimeter was about 2 degrees C, 2.5 degrees C, but not in the loop current. So that just means that there's a lot more heat and it's more sustained. That's the other part. So these areas sustain the heat flux. What we are finding with heat flux calculations based on atmospheric measurements from research aircraft is that we're seeing a lot of high heat flux right along the frontal structures. You know, where the air, where you go from cold to warm or warm to cold, right around the fronts. That seems to where be the action is for a lot of these tropical cyclones. So we're looking at that in detail from based on our NSF work.
Okay, thank you to our speakers very much. Very thought-provoking presentations. Really appreciate it. Very timely, of course. So Kirsten or Jorge, I'll turn it back over to you. I don't know if you want to take an extra 5 minutes or how you want to handle the break, but thank you.
Yes, I do want to echo thank you to all of the speakers. I really enjoyed all of the talks and discussion. And we do have a little bit of time at the end of the meeting. If you have additional follow-up questions or anything else you'd like to bring forward, we will have time for some more discussion. So definitely stay tuned if you have more thoughts or ideas about this. I think that we should still stay with a 15-minute break. Ish, 12 to 15 minutes. Let's say 1:08, come back. That would be, sorry, 2:08. I'm in Central Time. 3:08 Eastern Time. We'll come back and start up then with Ruth's panel. So thank you, everybody.